So this video we're going to be talking about rational functions and what's called points of discontinuity, and kind of basically how to find them, whether they're a zero, a vertical asymptote, or removable discontinuity, also known as point discontinuity. And so what I'd like you to do is I'd like you to write this equation down, p of x equals x squared minus 3x minus 40 all over x squared plus 16x plus 64. We're going to do 4 problems. Hopefully by the end of the 4 problems you'll understand what a zero is, what a vertical asymptote is, and what a point of discontinuity is, also known as removable discontinuity. But you also need to know how to factor. And so what we're going to do is we're going to factor the numerator. All right, we're going to factor the numerator. And we're going to find two numbers that add together to equal negative 3 but multiply together to equal negative 40. And that's going to be x minus 8 and x plus 5, because negative 8 plus 5 is negative 3, and negative 8 times 5 is negative 40. And then we're going to go ahead and we're going to factor the denominator. All right, and the denominator, it factors to x plus 8 and x plus 8. So we have everything factored. In order to do this, you've got to be able to factor things. It makes it so much easier. Now, from the last video we talked about, we said, hey, anything that makes the denominator equal to 0 is what's called a vertical asymptote. So there is one number right here that we could plug in here and here, a negative 8, that would create what's called a vertical asymptote. So I'm going to say we have a vertical asymptote at x equals negative 8. All right? Now there's a number that we could plug in here to make the numerator equal to a 0, and that number is an 8. So we can actually have a 0 in the numerator at x equals 8. And you can also have another 0 in the numerator at negative 5. So we have another 0 at negative 5. And so these are going to be the answers that I'm going to fill in. I'm going to say we have a vertical asymptote at x equals negative 8, so I'm going to fill that in. And then we have a 0 at negative 5, and we have a 0 at positive 8. Now before I do that, what I'd like to do is I'm going to go ahead and type it into the Khan Academy so you can clearly see the zeros and the vertical asymptote. Type into Desmos, my apologies. Let me pause it real quick and I'll type it in. Alright, so I've typed in our original function right here, x squared minus 3x minus 40 over x squared plus 16x plus 64. And I've also typed in x equals negative 8 because that's our vertical asymptote. You can kind of see right that, go and delete that real quick so you can see right here that is your vertical asymptote. And we also have two zeros. Check it out. I got a 0 at negative 5 and I have a 0 right here at an 8. So that kind of gives me a little bit of confidence when I'm typing it in that I did everything correctly. So we had a vertical asymptote at negative 8, we had a 0 at negative 5, and we had another 0 at positive 8. Okay. Let's go and take a look at the next one. We got a whole bunch of numbers we got to worry about here. We have zeros, vertical asymptotes, removable discontinuity. Go and write this problem down, and you better know how to factor it. So we're going to go ahead and get this sucker factored. So I'm going to go ahead, you write it down, and then I am going to factor it right here. Up here, we're looking for two numbers that add up to 10 but multiply together to equal 21. That's easy. That's going to be x plus 3 and x plus 7. And then down here it says two numbers that add up to negative 10 but multiply together to equal a positive 16. I'm going to put x minus 2 and x minus 8. And how do you check it once again? Just do they add together to equal the middle coefficient and multiply together to equal the last constant there? And negative 2 plus negative 8 is negative 10, and negative 2 times negative 8 is positive 16. So it looks like this time we actually have two vertical asymptotes. We have two numbers that we could plug in to make this denominator equal to 0. One of those numbers is an 8, one of those numbers is a 2. So I'm going to say we got a vertical asymptote at x equals 2. We have a vertical asymptote at x equals 8. And then we got a couple of zeros. What number would I plug in for the numerator to make it equal to 0? Negative 3. What number would I plug it in right here to make it equal to 0? Negative 7. So I have two zeros. You're probably wondering, well, what is removable discontinuity? We haven't had a problem yet, but I guarantee you we're going to get a problem with removable discontinuity. Just haven't gotten it just yet. But we'll get there. In fact, this video will not end until we get some removable discontinuity. I'll tell you that. We're going to find some removable discontinuity before this ends. Right now we're just finding some vertical asymptotes and zeros. So there we go. There's our zeros. There's our vertical asymptotes. So we got a 0 at -7. We've got a 0 at -3. We've got a vertical asymptote at a 2 and an 8. And we hit check. All right. So, by the way, if I type this in, and I'll go ahead and type it in real quick. It won't take long. Oh, don't want to go down that far. There we go. We'll go ahead and type it in. I will plus 10x plus 21, and then this was a minus 10, and then a plus 16. All right. So what I'm going to zoom out just a little bit so you can see we have a couple of zeros. We have asymptotes. We got one at an 8 right there, and then we also have another one at x equals 2. So we have 2, change colors there. There we go. We have 2 vertical asymptotes, one at a 2 and one at an 8, and you can also see our zeros here. We got a -3 0. And we got a -7 0, so you can see your zeros as well. All right, let's see if we have some holes or points of discontinuity, also known as removable discontinuity. All right, so first step, what are you going to do? You're going to factor. So we're going to just go ahead and get this nice and neat, factored out. All right, so right now we're looking for 2 numbers. Now, if you forgot how to factor, you're looking for 2 numbers that add together to equal a 4. And those same 2 numbers multiply together to equal a -32. And so you can clearly see that's going to be an 8 and a -4 and an 8 and a -4. Because 8 plus a -4 is 4, and 8 times a -4 is -32. So put x plus 8 and x minus 4. Now, in the denominator, we're looking for 2 numbers, right, that add together to equal -8. But those exact same 2 numbers multiply together to equal 16. Well, that, of course, is -4 and -4. All right, so helpful if you know your addition and subtraction and multiplication and division facts. Makes this life a lot easier. So we're going to put x minus 4 and x minus 4. All right, so this is the part that gets a little tricky because I want you guys to notice something. Because there's some rules that, like, what's more important than what. So here we go. So right now, upon first inspection, I want you to notice that these cancel out. And whenever those cancel out, it creates a hole in the graph. However, if you have an asymptote at the exact same point, which is at a 4, then the asymptote will trump the hole. Because basically, an asymptote's full of holes. It's just a whole bunch of holes all made into a long line of asymptote. Okay? So let me explain to you real quick. Let's say, for example, I'm going to do a different function. I'm going to call it f of x equals. And we're going to use a very similar, I'm going to put x plus 8. I'm going to put x minus 4. I'm going to leave this as x minus 4. But what if we had, instead of an x minus 4, we had an x plus 4? Then we'd have 3 different things happening in the graph. 1, these cancel out, and that's going to actually create what's called a hole, known as a removable discontinuity. So I'm going to put, we have a removable discontinuity at x equals a positive 4, because 4 minus 4 is 0. Next thing we're going to look at, we're going to look at the 0, which anytime you make the numerator equal to 0, we can make the numerator equal to 0 at x equals -8, but nothing's been canceled out. So we have a 0 at x equals -8. And last but not least, we have a vertical asymptote at x equals -4. So what I'd like to do is I'd like to show you what this looks like in a graph. So we have 3 things happening in this function. Okay? So I'm going to go ahead and type that in so you can see it. I'm going to clear this out, clear this out. I'm going to get this factored out. Change that to f of x. And let me go ahead and get that factor. We have parentheses. Let me delete this. All right, I think that was plus 8. We had x minus 4. We had, and then in the denominator, we had an x plus 4 and an x minus 4. Okay? So if we look at this, we have a hole at 4. When we look at the table will help you kind of know where different things are. So if I type in a -8, you clearly see that -8 is a 0. If I type in a 4, you're going to see it as undefined. If I type in a -4, you're also going to see it as undefined. So it's not going to tell you whether it's a hole or whether it's an asymptote. This is where you have to know the rules. Right here, let me go ahead and zoom in. Okay? Right here at a positive 4, I want you to look at it real quick. Do you see? Can you see that hole that's right there? Boom. Do you see that? That's what's called a removable discontinuity. That is a hole. Now, as soon as I let go of the mouse, you're not going to see it. But I'm holding it right there. That's what's called a hole. An asymptote is something that is a vertical asymptote that goes straight up and down. That's at x equals -4, which is right here. This is an asymptote that goes straight up and down. This is a hole. And then -8 is the 0. So hopefully you can see that and understand what I'm talking about. That when one of them cancel out, that creates a removable discontinuity, and that's also referred to as a hole. So that's a hole. This is referred to as a 0. That's referred to as a vertical asymptote. But here's what happens with us. We have a hole. Unfortunately, we also have an asymptote at the exact same point. So what trumps a hole? An asymptote. Okay? So what we're going to do here is I'm going to show you this equation. Okay? So I'm going to change this to another x minus 4. And I believe that's what we had. We had x plus 8, x minus 4. Yeah, here we go. So now, look, we don't have a hole. We just have an asymptote. Where is our asymptote? We have an asymptote right there at a 4. And if you zoom out, you can clearly see you have an asymptote at 4. And so that's why on this problem, we are going to say we have a 0. All right? We have a 0 at -8. All right? We have a 0 at -8. But we have a vertical asymptote at x equals 4. All right, let's do one more. Okay? So what I say, first thing we got to do is we got to factor. So we're going to go ahead and factor. Alright, so in this particular one, we're looking for two numbers that add up to 5 but multiply together to equal -14. So we're going to say x plus 7 and x minus 2, because 7 minus 2 is 5, and 7 times -2 is -14. And then down here, we're looking for two numbers that add up to 4 but multiply together to equal -21. So we're going to say x plus 7 and x minus 3, because 7 minus 3 is 4, but 7 times -3 is -21. This is a perfect example, because this has everything. This has zeros, it has vertical asymptotes, and it has removable discontinuity. So here we go. First thing we're going to find is the easy one right here. We have a 0. We have a 0 at 2. So we have a 0 at x equals 2, because it makes the numerator equal to 0. We have removable discontinuity because these cancel out. And where do they cancel out? What makes that equal to 0? A -7. So we have a removable discontinuity at x equals -7. All right, because -7 plus 7 is 0. And last but not least, we have a vertical asymptote. We have a vertical asymptote at 3. So this is awesome. We get to choose all 3 answers in this problem, which makes my life a lot easier because that means I don't have to do another problem. So step 1, what should you do? Factor. Step 2, see if anything cancels out. If anything cancels out, you could have what's called a removable discontinuity unless you have an asymptote at that exact same point. Then you got to choose the asymptote over the removable discontinuity. Okay? So these are going to be my answers. I have one more quick example. What would happen if you had, let's say, x plus 5 times x plus 5 over, say, x plus 5? Okay? Now, what happens here? These would cancel out, and you would have a removable discontinuity at x equals -5. But wait a second. Couldn't you plug in a -5 and make it equal to 0? Yes. But as far as the powers go, here's the most powerful. Number 1, the most powerful is the vertical asymptote. Number 2, the second most powerful is the removable discontinuity. And then finally, the last, the 0. So what I'd have to choose in this one is I would actually have to choose, we have removable discontinuity at x equals -5, and you couldn't choose a 0 on that one. So this is just an example. It has nothing to do with this particular problem, but I've seen them where you have two of these where one of them cancels out and you're still left with that. So this one would only have a removable discontinuity at -5. But we're going to go ahead and plug these in. We had a removable here. We had a 0 right there. And we had a vertical asymptote there. Make sure. Yep. And there we go. All right, so we're going to take a look at step-by-step solutions, see what they do. Looks like, oh, there they go. They cancel them out. And it lets you know how to identify the asymptotes and how to identify the zeros. And so if you miss one, go through it. You'll see the correct factors. You'll see how to do it step by step, and it will only help you if you read through it and write things down in your journal. You'll have a good day. Bye-bye.